Okay, so this is our problem for today. You are required to obtain your I using Thevenin's and Norton's theorem. So by Thevenin's theorem, your I is the open circuit voltage divided by the looking back resistance plus your load resistance RL. And by Norton's theorem, your I is the short circuit current times the looking back resistance all over R sub O plus R sub L, wherein by inspection our RL should be the resistance where your current is to be obtained. In this case, it is 2 ohms. Okay, so let us start to find the open circuit voltage. Okay, so how do we obtain the open circuit voltage? The open circuit voltage is obtained by removing your load resistance RL and finding what will be the voltage that will exist across these points. Supposing that this is terminal 1 and terminal 2. Okay, let us try to redraw your figure for clarity. Plus minus. Okay, this is your terminal 1 and terminal 2. 5 amperes, 24 volts, 8 ohms, okay, 6, 4 ohms, 3 ohms, and 8 volts. Let us try to find the voltage that will exist across these points. But first and foremost is you need to make an assumption which one of these terminals is positive and negative. And let us assume that terminal 1 is positive and terminal 2 is negative. Okay. The open circuit voltage is easily obtained by applying your loop analysis. The circulating current here is negative 5, correct? The circulating current in the other one is A, and this one is B. So we have only 2 circulating currents. So if we start by applying your loop current equation at loop A, this will be 8 plus 6, 14 plus 3 is 17. So that is negative 17A plus 3B, correct? Plus 6 times negative 5 plus 24 is 0. So if we simplify, this is negative 17A plus 3B is positive 6. Correct? Ayan. First equation. And our second equation is obtained in the same way, no? Loop current equation at loop B. This is 3A minus 7B. From plus to minus, that is negative 8. We transpose that in the other side, it will become positive 8 volts. This is your second equation. So we already have 2 equations. You can easily solve this either by manual calculation or using your calculator. So if you try to now to solve what is A and what is B, your A is negative 0.6 amperes and your B is negative 1.4 amperes. How do we obtain now the open circuit voltage? Okay, your open circuit voltage is between points 1 and 2. That is easily obtained by applying your KVL following this closed path. Okay, KVL at loop X. Okay, so KVL at loop X, you will now have from minus to plus, that is positive 24 minus 8 times A. The value of A is negative 0.6. From plus to minus, minus B sub O, then you return to 0. So the open circuit voltage is equivalent to 28.8 volts. That is now the open circuit voltage. Okay, nalagay natin dito. B sub O is 28.8 volts. The next thing that we should have is the looking back resistance. Okay? Loop current analysis is just one of the options which you can use if you will try to find the open circuit voltage. You can make use also of your Kirchhoffs. Through the use of Kirchhoffs, this will be involving 1, 2, 3, and 4 unknowns. Okay? Pwede rin, you can also obtain or use your superposition and others. Okay? Let us try now to find the looking back resistance. Okay? In finding your R sub O, first step just the same is you are going to replace all your energy sources by their equivalent internal resistance, which is ideally replace your voltage sources by a short circuit and replace your current sources by an open circuit. Okay? That is what the theorem states. Okay. So let us try to redraw your figure. We replace this with short circuit as well as with this, also with a short circuit. And short circuit, and your 5 amperes by an open circuit. So this is how your open circuit will look like. There. Okay. So what is our R sub O between points 1 and 2? Okay. For easy analysis, let us just remove this excess terminal and recognize how are these points are all related. Okay? 4 and 3 are in parallel. This parallel group is in series with 6 ohms. This series parallel group is in parallel with 8 ohms. Supposing that this series parallel group is denoted by Rx. So what is Rx equal to? This is 4 times 3 divided by 4 plus 3 plus 6 ohms. And that is equivalent to 7.714. 7.714 ohms. So your R sub O is just equivalent now to the parallel combination of Rx and 8 ohms, which is 8 times 7.714 all over 8 plus 7.714. The looking back resistance is 3.927 ohms. So we already have the value of R sub O. So we can obtain your I. Your I is the open circuit voltage of 28.8 divided by R sub O of 3.927 plus RL, which is equivalent to 2 ohms. This will give you a value of I which is 4.827 amperes, obtained by the use of Thevenins. Lagyan natin dito, R sub O is 3.927 7 ohms, having a value of I of 4.827 amperes. Okay? That will answer for Thevenins. How about for Nortons? Okay? Let us try also to solve the problem using Nortons. Okay, let us redraw your figure again. The same figure, there is only a slight change, no? For our I short circuit, instead of having this short circuited, open circuited, we will now have to replace your 2 ohms by a short circuit. This is our terminal 1 and terminal 2. Let us replace this with a short circuit and try to obtain what is the current that will flow into this short circuited part. So this is 5 amperes, 8 ohms, 6, 4, 3, 24, and 8 volts. Okay? Let us try to approach again the problem by loop analysis. So far, that is the most convenient. Okay? Assuming that this is your circulating current A, we have another circulating current B, another circulating current C. The circulating current in this part is a giveaway, that is negative 5 amperes. So we needed only 3 equations, which can be easily derived. Let us start. Loop current equation at loop A. This will enable you to obtain your A, that is negative 8A plus 24 is 0. So your A is 3 amperes. So you already have your A. And for B, loop current equation at loop B, that is negative 9B plus 3C plus 6 times negative 5, correct? Negative 9B plus 3C plus 6 times negative 5 is 0. So this is negative 9B plus 3C is 30. This is equation 1. And doing the same at loop C, loop current equation at loop C, that is positive 3B, correct? Minus 7C minus 8. If we transpose that in the other side, it will become positive 8. So that is equation 2. And you have 2 equations containing 2 unknowns. And you can easily find its value, the value of B, as well as the value of C. Your B is negative 4.333 amperes, and the value of C is negative 3 amperes. This time, you can now obtain the value of the short circuit current. Short circuit current is equivalent now to the difference between your A and your circulating current B. A being 3 amperes and the value of B is negative 4.333. So the short circuit current is 7.333 amperes. Okay? So by Norton's, your I is the short circuit current of 7.333 times R sub O, that is 3.927 divided by 3.927 plus your RL of 2 ohms. And you will see that the value of I is the same, which is 4.86 amperes. Parehas lang. Now, another quick check on how you can validate your short circuit current together with your open circuit voltage is this. If you try to find the ratio of the open circuit voltage to the short circuit current, you will see that it is equivalent to R sub O. How do we come up with that relationship? Okay? Dito tayo. From Thevenin's, your I is equivalent to V sub O divided by R sub O plus RL. And by Norton's, this is I short circuit times R sub O divided by R sub O plus RL. Why is it that we equate the two equivalents for Thevenin's and Norton's? As you can see, under Thevenin's, we are solving for I, and by Norton's, we are also solving the same value of I. We are expecting to obtain the same value of I under Thevenin's, which is also equivalent, and it must be equivalent by using Norton's. That is the reason why we equated your I from Thevenin's to the I from Norton's. Your denominator now will cancel, giving you the relationship between the open circuit voltage with that of the short circuit current, which is the ratio of the open circuit voltage to the short circuit current is your R sub O. Okay? So this is how you are going to use your Thevenin's and Norton's theorem in a problem. Circuits containing dependent sources. Okay?